1. Alright. So we have now established what it means to be Riemann integrable in terms of Darboux sums. We've also established that Riemann sums are going to work the way they did before. We've got the epsilons, we got the deltas, we got the mesh. We're good. So let's go ahead and prove that some pretty basic facts about Riemann integration are still true. So first of all, let's prove that a constant function integrates to what you think it should integrate to, because a constant function, well, this would be representing the area of a rectangle, so it should be the base times the height. Here the height is alpha, the width of the base is the length of the interval, and indeed, we can make this work out. So, given any partition, the lower and upper Darboux sums are just going to work out to be alpha, because, right, these are representing the imps on the subintervals and the sups and the function's constant, so the imps and the sups are just alpha. So when I look at the lower and upper Darboux sums, I will just get A, alpha times B minus A, and therefore the upper and lower Darboux sums are in fact equal to each other, and they're equal to alpha times B minus A. So, alright, there you go. Integrating a constant function does what you expect it to do. Nothing crazy. Alright. Following that, let's now prove that scaling a Riemann integrable function gives you a Riemann integrable function, and the integral is the scaled integral. So in other words, I could pull scalars out of my integral. Alright, so how am I going to do this? Well, so first of all, we'll take care of a trivial case. If the scalar in question is 0, then it's the constant function 0, and by the previous proposition, we've already established that that is indeed Riemann integrable, and its integral is 0. And there you go. It worked out. Pretty cool. Alright, so now what happens when alpha is non-zero? Well, alright, I want to prove that alpha f is Riemann integrable, and its integral is what I want it to be. And here's where using Riemann sums is going to be a good move. So, given an epsilon, we know there is a delta, so that given a partition, the Riemann integral itself gets within the epsilon of these partitions, and here I've chosen my epsilons to be, hey, the absolute value of my alpha, because guess what? I can multiply that thing across the board, and here I'll have that alpha times the integral is within alpha multiplying my function, and that's less than epsilon. So, hey, given an epsilon, we've proven that there is a mesh size, so that any of these partitions, the Riemann sums, gets within epsilon of this thing here. That guarantees that you are in fact Riemann integrable, and your Riemann integral is this thing. Hey, look at that. There you go. Scaling a function keeps you Riemann integrable, and its Riemann integral is exactly what you expect it to be. Given an epsilon, we found a delta, so life was good. Pretty cool. Alright, so hey, we did, if you scale a Riemann integrable function, you remain Riemann integrable. How about adding them? Indeed, if you add two Riemann integrable functions, they are indeed Riemann integrable, and their integral is exactly what you want it to be, the sum of the integrals. So, right, our favorite phrase in mathematics, the x of the y is the y of the x. The integral of the sum is the sum of the integrals. Let's actually prove it. Alright, and basically this will be exactly how we just prove that scaling works the way we want. Given an epsilon, we can create partitions. I have two things, so I'm going to have to do epsilons over 2's. Right, and note that this epsilon over 2 is going to have a delta associated with it. This epsilon over 2 will have an eta associated with it, so obviously we'll go ahead and just take the minimum of those two things. We'll call that nu here. And so any partition that's within nu will be within delta and eta, so that then this Riemann sum is within epsilon over 2 of this Riemann integral, and this Riemann sum is within epsilon over 2 of this Riemann integral. And note that inside we've got that, and so here we see the Riemann sums for f plus g are indeed within epsilon of the sum of the Riemann integrals, meaning that the sum is Riemann integrable, and its Riemann integral is exactly what we want it to be, the sum of the integrals. Hey, so we've proven that I can scale a function and remain Riemann integrable, and I can add functions and remain Riemann integrable, and their integrals correspond nicely. Nice. Okay, so, hey, we got scaling functions as Riemann integrable, we got adding functions as Riemann integrable. What about multiplying them? Well, we know the product of Riemann integrable functions is Riemann integrable from our calculus days, but as we also learned from our calculus days, the integral of a product doesn't exactly have a nice integral. So here's why, while the Riemann sums work out great, sometimes they're not theoretically the best thing to work with, and here we'll see Darboux sums come in and kind of pick up the slack. But before we get there, we're going to need a couple of other results. So first of all, let's go ahead and prove that if you've got two Riemann integrable functions where one is bigger than the other, then the Riemann integral, it doesn't get bigger, right? Okay, so you got your partition. F is less than or equal to g, so the integral is less than the upper Darboux integral, which means it's less than those soups, but those soups are less than the soups for g, so we get that. And there you go. This integral is a lower bound for all of the upper Darboux sums of g, which means the upper Darboux integral is less than or equal to it, and there you go. Sweet. All right, now we will demonstrate that absolute values will behave, and in fact the absolute value of the integral is less than or equal to the integral of the absolute value. Now this is one we don't really deal with in calculus, but for us it's going to be, yeah, we're going to need this. All right, so how are we going to do it? All right, well, given an epsilon, note that here I'm proving Riemann integrability, so I'm going to have to do something showing that partitions are behaving. And I'm not going to get that the Riemann integral is equal to anything, but I will get an estimate for it. All right, so because I don't exactly know what the Riemann integral is going to equal, I'm going to have to rely on Darboux sums and just demonstrate that, well, we are Riemann integrable, and I don't particularly care what the Riemann integral is equal to. All right, so given epsilon, there is a partition so that the upper and lower Darboux sums with an epsilon of each other. All right, I claim that the upper and lower Darboux sums of the absolute values are then less than that. So that's less than epsilon, and that'll get me the integrable part of the proof. All right, so how do I do that? Well, pick any 2 points in the partition. Those 2 points are bounded above and below by these soups and imps, and note that would mean that in absolute value, these don't exceed the difference of the two. Alright. Which means that now, when I look at the absolute value of this minus the absolute value of that, by a rearranging of the triangle inequality, I know that this does not exceed that absolute value, which is less than or equal to this, which is less than or equal to that, and oh, hey, looky, looky. We know that from this we can rearrange things and get that the absolute value of f of y is less than or equal to this, meaning that when I look at the actual supremum of the absolute value of f on these partitions, they're not going to exceed this quantity. And you can pull a similar move for the f of z term. And there you go, rearranging the terms here in the inequality will then give me that the soups minus the imps of the absolute value of f do not exceed the soups and the imps of f minusing itself. That gives me that the absolute value of f is in fact Riemann integrable. All right. Because then when I look at the lower Darboux sums, I already know that each one of these soups and imps are less than or equal to this difference of soups and imps. And there we go. All right, and now furthermore, since we know that my function will always be less than or equal to its absolute values as such, and we just proved the absolute value is Riemann integrable, and I can pull in -1 on my integral, I know that my integral here is bounded above by that and bounded below by this. So my integral is within the plus and the negative of that integral, which means that it's within, its absolute value is trapped between the two. Nice. So hey, good thing we proved that Riemann integrability is monotone, so if I have a function less than or another, the Riemann integrals are behaving nicely. All right, so again, our quest here is to prove that multiplication works out the way we want it to. Now, before we got there, we did inequalities, we did absolute value. Naturally, now we'll take care of squaring before we get the multiplication, and you'll see why we're going to want to do squaring first. Alright, so indeed, let epsilon be greater than 0. I want to prove that f squared is Riemann integrable. Now, what's the trick going to be? Well, okay, my function's bounded, so there is a b, so the absolute value of that function does not exceed it. And thus I can find a partition, because I know my absolute value is integrable. I can find a partition so that gets to epsilon over twice b. And all this material here will become clear in a moment. My claim is that the sup of the absolute value squared will line up with the sup of the normal with the sup of f squared. Likewise, the inf squared will be the inf of f squared. Okay. And as per usual here, I'm only going to take care of the first equality. Yeah. And note that for any x hanging out on a subinterval, we know that f squared is less than or equal to this. So if I square root both sides, which I can do, this here will give me just the absolute value, and this will just give me the square root of that. So that means that when I look at the sup of my absolute value on my subinterval, it's always bounded above by this, and thus I could square both sides. And to get the inequality in the other direction, well, note that the absolute value is always less than or equal to this thing, and then just squaring both sides will then give me the inequality in the other direction. Ooh, pretty cool. All right, now what? So now, when I look at the sup for f squared minus the inf of f squared, okay, well, I've already pointed out what these are equal to. And note, I've got a difference of squares squared going on here. Right, so we know what that's equal to. So, oh my god, cat. And actually, that's an extra squid. What is this doing here? Well, what's going on? Hold on. Hold the fort. Right, we proved that. I think that's just left over. Yeah, so note here, we got that's equal to that squared, that's equal to that squared. So then when I look at the difference here, yeah, that's just an extra square. That was somebody getting pretty trigger happy with the squares there. All right, so let's fix that. That was me. It was me. I'm the problem. All right. I think I originally had. I'm trying to see where that square came from. But anyway, note that this is equal to that squared. That's equal to that squared. Hey, it's a difference of squares. That factors as follows. And then we chose these things to get twice of them. And indeed, they'll be less than or equal to twice this multiplied. And right, the 2 over. Right, so each of these is less than twice that. I'm trying, man, I'm having, oh man, there's a lot of notational joint. There's an absolute value supposed to be on there, right? And, right, note that, so we had one of these, and then this here, right, was rigged to be less than or equal to 2 times b. That was coming from, just from being less than or equal to. Yeah, right, yeah. So each one of these is bounded above by b. That's why we have twice b here, right? Because b is an upper bound for f, so it's bigger than the sup, and also bigger than the inf. That's where the 2b is coming from. All right, sorry about the brain fart that happened right there. I'm already 13 minutes deep in this video, so we gotta power through it. All right. Anyway, all right. So this part here is less than or equal to 2 times b, multiplying out that. All right, and then when we look at the upper and lower sum, we're adding up all of these things. And then now the sum here, there, will give me the upper and lower Darboux sums difference. And that's why we chose the partition to be less than epsilon over 2b, to ensure that at this point, it'll multiply and be less than epsilon, ensuring that if you're Riemann integrable, then squaring keeps you Riemann integrable. All right, and now equipped with all of this, we can in fact prove that multiplication of Riemann integrable functions remains Riemann integrable. And again, note, at no point here did we establish any formulas for this, because as we've learned from our calculus days, there is no formula for the Riemann integral of a product. However, a product can be written as a difference of appropriately chosen squares and scaled. And we've already proven that if you're Riemann integrable, sums are Riemann integrable, squares are Riemann integrable, and scaling and adding functions are Riemann integrable as well. So there you go. Man, maybe when we try to fix the Riemann integral, having this idea in the back of our head is going to make some proofs a little easy. All right, and speaking of all of that, let's finish things off with the big thing, the final part of the slides here, which is that continuous functions are indeed Riemann integrable. All right. Now, of course, from calculus, we know that there's some antiderivative stuff we can do, but we're not going to worry about derivatives in this class. All right, but let's actually prove that if you are indeed continuous, you are Riemann integrable. All right. And last time when we were talking continuity, we made a big stink about uniform continuity. So, you know. All right, so first of all, note that f's bounded, which are precisely the functions we're allowed to Riemann integrate. Let epsilon be greater than 0. I want to prove that there are partitions that are behaving. Well, let's go ahead and let eta be epsilon over twice the length of the interval, and note that this is just rigged so that eta times the length of the interval is in fact less than epsilon, so we're going to go for a uniform partition, uniformly spaced one, and we're going to rig it so the spacing is the way we want it to be. All right. Now, continuous on a closed-bounded interval means that we are a continuous function on a compact set, which means we are uniformly continuous, so there is a delta, so that my outputs get within eta for any inputs that are within delta, and that's uniformly across the board. So I can find an n so that the length of the interval over n gets less than delta, so I'm going to now create the uniformly spaced partition. It'll be less than delta in mesh there. Okay, and note in particular that the deltas, right, they're strictly less than the delta x's are strictly less than that delta there. And note further, since f is in fact continuous on these closed-bounded intervals by the extreme value theorem, it obtains its infinite, it obtains its sup. So the lower and upper Darboux sums are in fact actually Riemann sums in disguise. That's quite nice. All right, and in particular then, that means the upper and the lower, the sup and the inf on the subintervals, because the inputs are going to be stuck between the subintervals, and the subintervals width is chosen less than delta, we know that my function's outputs here are going to be within eta of each other. Means these things are within eta of each other. So when I go to the upper and lower Darboux sums and look at their difference, it is precisely this. These were rigged so all of these are less than eta. That's eta times the sum of the deltas, which is b minus a, which was rigged so that eta times b minus a is in fact less than epsilon, and there we go. Continuous functions are nice and Riemann integrable. And uniform continuity was the key. Good thing we spent a bit of time and talked about that. And there we go. Everything about Riemann integration that we need has been established. So we've got the epsilon delta version of Riemann integration. Given an epsilon, there is a delta, so partitions are behaving. We, of course, set it up using upper and lower Darboux, which revealed that there are functions that fail to be Riemann integrable. Dirichlet's function. And as we noted, Dirichlet's function failing to be integrable is kind of a problem because it seems like it should be, because there's a limit we can set up. But we got to formalize that limit of those sequence of functions that we talked about day one of the course, so that's the goal in the next video.